Hello everyone. The aim of this video is to give you an overview of some typical carbon-carbon forming reactions. Specifically, I'm going to be focusing in two reactions, the Wittig reaction and the Diels-Alder condensation. This table from March Organic Chemistry gives a really nice overview of some typical reactions that allow the formation of carbon-carbon bonds. Quite a few of them hopefully will be familiar, either because they are straightforward nucleophilic substitutions or because you have studied them before. For example, when you looked at organometallic compounds, or when you looked at Friedel-Crafts acylations and alkylations when you did the chemistry of benzene. The two that maybe are not familiar in this table are the Wittig reaction and the Diels-Alder cyclization, which are the focus of this video. In a Wittig reaction, you treat an aldehyde or a ketone with a phosphorus ylide. This reagent is commonly known as Wittig reagent to produce an alkene. The stability of the Wittig reagent varies depending on what makes that Wittig reagent. Simple reagents that have substituents like hydrogen or alkyl groups are highly reactive. But when they have an electron withdrawing group in the structure, in the carbon of the alpha position, then it is much more stable because you can have resonance forms. You can have a delocalization of that charge. So for example, if you imagine a Wittig reagent with a phosphorus and 3 phenyl groups, and the phosphorus has a positive charge. You've got here the negative charge over the carbon, and let's say that has a carbonyl group here in this alpha position. Well, you have the possibility of a resonant form, which would be the formation of a double bond between these two carbons and the oxygen sustaining that negative charge. So that gives you the possibility of stabilizing that carbon ion, and the resulting Wittig reagent, the resulting ylide, is much more stable than if you did not have that carbonyl group in the alpha carbon. How to prepare a Wittig reagent? Well, there are a few that are commercially available. However, most Wittig reagents are phosphorant. Well, most phosphorants, which is what a Wittig reagent is, can be quite reactive. They hydrolyze and oxidize easily, so they often need to be prepared in situ before the reaction takes place and in absence of air. So to prepare a Wittig reagent, you need to use a phosphonium salt, which whatever groups you are interested on putting into your compound, and treat it with a base. Sometimes you need a strong base, like for example, you can use N-butyl lithium, and depending on the reagent, sometimes a weaker base or sodium hydroxide or even something like sodium carbonate is enough. To prepare a phosphonium salt, you typically use a triaryl phosphine, a phosphine with 3 phenyl groups, and an alkyl halide, which contains whichever group you are interested on adding to your product. This is the mechanism. This is a schema reaction of the mechanism of the Wittig reaction, and as you can see, it starts with a typical nucleophilic attack. So the negative charge from the carbon attacks the partial positive charge of the carbonyl group, and you form an intermediate called betaine. So there is a free rotation around the carbons, so you can form intermediate 4. And if you look at the position of intermediate 4, you have the phosphorus and the oxygen close enough, and one with a positive charge and one with a negative charge, to form a bond. And that's how you make compound 5. And compound 5 is called a is called oxophosphatane. And then there is an elimination reaction in which you eliminate the phosphine oxide, which is this compound here, in this case triphenyl phosphine oxide, and you form an alkane. And in this case, the alkane that you are forming is the Z alkane. So E-alkane, Z-alkane. Now you're going to have a cis or a trans isomer. Well, sometimes you have one of them primarily. Sometimes you will have a mixture of both. And it depends on the Wittig reagent, on the stability of the Wittig reagent. When you have a Wittig reagent that contains an stabilizing group, for example, that might have a carbonyl group in that alpha carbon withdrawing from that allows you that extra resonant form, or Wittig reagents that are formed from trialkyl phosphines, you tend to have the E-alkane. When you are using triaryl phosphine, so phenyl groups rather than alkyl groups in that phosphine, and without a stabilizing group, you often have either the Z isomer or a mixture of both. There are things like the base you use to generate the Wittig reagent can play an effect, and for example, something like the use of lithium salts when generating the Wittig reagent can also affect the stereochemistry. The Diels-Alder cyclization is the formation of a cyclohexane from a condensation of a carbon-carbon bond of an alkane to a 1,4 conjugated diene. So you have a carbon-carbon bond with, or a simple carbon bond or with a particular functional group attached to it, and you make it react with a 1,4 conjugated diene. And reasonably easily, sometimes you have to heat up, etc., you form this cycle. So you've got an electron from each of the double bonds, and you end up with a cyclohexane. You have your functional group here, A, if you have one, and the cyclohexane, the double bond forms in these two carbons. The substrate that reacts with the diene is called a dienophile. Dienophiles have a carbon-carbon double bond, and they can have extra groups attached to them. And Z or Z prime in this notation are electron withdrawing groups. So think of groups that will pull from the charge of that double bond. A carbonyl group, a carbon with an amino group attached to it, an aryl group, benzene ring, halogens, an hydroxyl group attached to a carbon, or this is a nitrile, or even another carbon-carbon double bond. So you are withdrawing electronic charge from that double bond. And it's a reasonably easy reaction. Nearly all conjugated dienes and will undergo a Diels-Alder cyclization. And you can have some really interesting products. So because you can do it with open dienes, but also you can also do them with cycles and get quite complicated structures. So for example, if you have a cyclopentadiene, and you make it react with, let's say, your electron withdrawing group, in this case is a nitro group, you can have the reaction. So the electrons go here, here, and here, and you end up with the cyclohexene that has formed here, and you still have that part of the molecule. So it's an interesting way of forming interesting structures, three-dimensional structures, using carbon atoms. Diels-Alder reactions, condensations, are used widely in all fields of chemistry, synthetic chemistry, including pharmaceutical chemistry. So for example, this image from a review from 2020 on how to synthesize tetrahydrocannabinol derivatives, THC derivatives, has a section on how to use Diels-Alder cyclizations to obtain THC derivatives. And if you look at specifically at compound 57, one of the intermediates of reaction to synthesize this THC derivative, that is the result, this part of the molecule is the result of a Diels-Alder condensation. So you have the dienophile here, and you have the 1,4-diene, and again you've got the changes of the the breaking and making of new bonds using the 3 double bonds, and you end up with this structure. And in this case, you have the electron withdrawing group would be this section of the molecule. So this is all for this video. I hope it was useful, and if you do have any questions, please do email me or post in the discussion board for the module. Thank you very much for watching.